Hello viewers, in today's class we are going to discuss one important conceptual problem from limits involving the fractional part function and greatest integer function, right? So here we'll solve this problem, that is if limit x tends to 2 minus, right? So here the negative sign shows that we have to find the left hand limit of this function when x approaches to 2, right? So limit x tends to 2 minus, and here we have fractional part of x minus 2 divided by greatest integer of x minus 2 is equal to e raised to iota mu over pi, where mu belongs to the set of real numbers, and we have to find the value of this number mu, right? So let us start, and first we'll find the value of this limit, right? So let us call this limit as L, and we can take it as limit x tends to 2 minus. Here we have fractional part of x minus 2 divided by greatest integer of x minus 2, right? So in order to solve this limit, what we will do, see here we have the point x is equal to 2, right? And we have to approach towards x is equal to 2 from the left of x is equal to 2, right? So what we will do, we'll take x is equal to 2 minus h, right? Where this quantity h is a positive quantity, and it is a very small quantity which lies between 0 and 1, right? So when x tends to 2, then obviously h tends to 0, right? So now this limit takes the form in terms of h as limit we have h tends to 0, and here we have fractional part of x minus 2. So for x we can write 2 minus h minus 2, and then we have the greatest integer of x minus 2. So for x we have 2 minus h minus 2, right? So let us simplify it. So we have limit h tends to 0, and here this 2 and this 2 get cancelled. Here also this 2 and this 2 get cancelled, and we have fractional part of minus h divided by greatest integer of minus h, right? Okay, so now we have simplified this limit to this form, and here we cannot directly substitute the value of h is equal to 0 in this expression, right? So in the numerator we have thus fractional part function, and in the denominator we have greatest integer function. So we'll here make use of the definition of fractional part function and greatest integer function. So now we know the definition of fractional part of function, that is fractional part of x, which is given by x minus greatest integer of x, right? So this is the definition of fractional part of x, and we know that the domain of fractional part of x is the set of all real numbers, and the range is from 0 to 1, right? So here we have fractional part of minus h. So what we will do, we'll write it like this. So limit h tends to 0, and we have minus h minus and greatest integer of minus h using this definition of fractional part function, and in the denominator we have the greatest integer of minus h, right? Okay, now here see, in the numerator we have greatest integer of minus h, and in the denominator also we have greatest integer of minus h. So now we'll use this inequality to assign a value to greatest integer of minus h, right? See here h lies between 0 and 1, right? So if we multiply throughout this inequality by negative sign, what we will get here will get 0, and then we have minus h, and here we have minus 1, right? And when we multiply throughout by minus 1, the direction of the inequality get reversed. So now we have minus 1 is less than minus h, and this is less than 0, right? So now from this inequality we see that minus h, it lies between minus 1 and 0, right? So minus h lies between minus 1 and 0. So from the definition of greatest integer function, the value of greatest integer of minus h is equal to minus 1, right? So now we can substitute greatest integer of minus h as minus 1. So we have limit h tends to 0. Here we have minus h, and then we have minus, and here we have minus 1 divided by minus 1, right? So simplifying it, we have limit h tends to 0. This is minus h, this is plus 1, and we have here minus 1, right? Now if we substitute h is equal to 0 here, now we'll get minus 0 plus 1 over minus 1. So this is 1 over minus 1, that is equal to minus 1, right? So the limit of this function when x approaches to 2 from the left of x is equal to 2 is minus 1, right? So the limit L is equal to minus 1. Now in the given problem we are given this limit is equal to e raised to iota mu over pi, right? Where I or iota is the complex number, right? So now L is given as e raised to iota mu over pi. So we can equate these two quantities. So we have now e raised to iota mu over pi is equal to minus 1, right? And remember we know that iota square or I square is equal to minus 1, right? Okay, now here in order to find out the value of mu, we'll make use of the famous Euler's formula, right? And Euler's formula goes like this, that is e raised to iota theta is equal to cos theta plus I sine theta, right? And see, if we take theta is equal to pi here, we'll get e raised to iota pi, and here we have cos of pi plus iota sine pi, and cos pi is minus 1, sine pi is 0, so we are left with minus 1 plus I times 0, that is equal to minus 1, right? So now this minus 1 can be replaced by we can write e raised to iota pi, right? So now we can compare these two numbers, right? So here we have e raised to I mu over pi, here we have e raised to I pi. So if we now compare, then we get mu over pi is equal to pi, right? And taking the product of these two numbers, we have pi times pi, that is pi square, right? So the value of mu is equal to pi square, right? So this is how we can solve these type of problems.